Hello and welcome everyone to our 7th tutorial video. So today we are going to create a supercell file from a unit cell structure, and then we will add some defects that could include like point defects like vacancy, interstitials, antisites, and also I will be considering some p-type or n-type donor acceptor like impurities. So let's start from where we left previously. So this is where we left. Clear this a little bit. So we completed step 8. Now let's go to the defect folder. So you can just copy paste it here. So what this will do, that we will be moving to the defect folder, and then as you can remember, I think, like here in the gallium nitride folder we have the defect folder and the unit cell folder, and in the unit cell folder in the structure oft we have the POSCAR file, and this POSCAR file actually holds the relaxed unit cell. So what this code will do is that it will try to extract that file and try to create a supercell structure. Okay, so if we just use this code 3 lines, then it will create the supercell structure in the defect folder. So I can just quickly copy it and run it here. As you can see, some of the information are also provided, like the supercell structure and all those information that we could actually see. Let me just go back to the defect folder. So as you can see, in the defect folder there is the POSCAR file. So this is the supercell structure that is automatically generated by the BIS, that is like the package that integrates PyDefect with VASP. So when you install PyDefect and BIS and run command from BIS, it will just use PyDefect materials project API and VASP to create this automatically. So this is a gallium nitride supercell with like 300 atoms, 150 gallium atoms, and 150 nitrogen atoms. So this is automatically created. And also here is the supercell info.json file. As you can see, these are some information that is actually provided. So in this supercell.json file, as you can see, if we just PyDefect print it, then we'll see that the matrix transformation is 5 by 5 by 3, which that means that our unit cell is actually multiplied 5 in x-axis, 5 in y-axis, and 5 in z-axis, or you can see in ABC parameters. The cell multiplicity is 75. There is also like types of symmetry, excuse me. Yeah, so there are also types of symmetry, cutoff radius, and also the coordinates. All these things are already provided. Also the oxidation stage and electronegativity are also provided. So this is where this information are in the supercell info.json file. Also one file is created named perfect. So this is the perfect, means like in this supercell, so in this supercell, as you can see, like all these atoms, or you could say in general, this whole file, it doesn't have any defects, right? It had a 150 gallium atom and 150 nitrogen atoms, so there is no defect. So this is a perfect supercell. So this is why there is a folder called perfect. We will also like use the perfect one and also the defected one to like have the comparative analysis. So to do that, let's start with the defect. So let's incorporate some defects to that. So to do that, we can use the PyDefect DS. So if you want to, like as I said earlier, if you want to know more about these commands, you can just quickly go to the PyDefect tutorial. I am actually following their own flow, and you will be able to like easily make a informative comparison and informative analysis, like what the different types of command is doing. Like for DS, it is defect set subcommand. So if you need any information or any further exploration about these commands, you can quickly come to PyDefect, their official website, and see it here from here. Okay, so let me just clear this thing and run this so I need to run this command PyDefect DS. So remember, I am in the PyDefect folder. I am here, and now let's run this command. and it will if we just come here, you'll see that there is a file create two file actually create one file is actually created, sorry, that is like defect in.yml. so if I just try to read this document, like what is actually happening here, to do that I can, let me just quickly close some folders, tabs, I don't need that. Yeah, so to quickly see that, what we can do is like we can PyDefect print this folder, print this file, sorry. So let's PyDefect print this file, and as you can see that these are like some uh, antisites are created. As you can see, gallium nitrogen antisite, so gallium in the place of nitrogen with the charge state from 0 to 6, and also nitrogen in the place of gallium from charge state -6 to 0, all these things. So let me just add this thing so that you can use it in your calculation. Let me just add this command so that you can have the, you can visualize the uh, defect. Okay, okay, let's come here. Yeah, so I have added these two lines so that you can see the defects. Okay, now I am going to add n-type silicon and p-type magnesium to my this defect directory. So remember, every time you add a new defect, new types of defect, you use this PyDefect ds command. For impurity, you use this PyDefect ds d silicon and magnesium. Like these are two impurities that I'm adding. So let's add this two also. I think there is a thing that both interstitial antisites and vacancy are actually created in this one command. So I need to just update this. For interstitials, you need to add it separately. I will show you in after a few steps. Few steps, not I would say like after a few minutes maybe. Okay, then after that, after you have added this like these impurities, let's also, after you run this calculation, as you can see, it is like 853. If I refresh it, so it's like 856. So a new defect.in is actually created or updated, you could say. So here, as you can see, gallium in the place of nitrogen, magnesium in the place of gallium, so all the impurities are also considered. So this basic command PyDefect ds is actually used to create antisites and vacancies. So vacancies are not are actually shown here also, as you can see. So vacancy and in antisites are here. Now for here also impurities, so you have three. Here you have only vacancy and antisites. Here you have vacancy, antisites, and impurities. Now the fourth and the final one is the like the the interstitials. So we'll also try to calculate interstitials too. But before that, we need to make sure we have some files. So let's come here, and as you can see, we are in this part. So let me just mention you something, that if you want to update any oxidation states, you can do that by this command. Also, if you want to know more about how you can change different types of oxidation state change, you can also refer to these documents, right? Like here they are using adding some data to their already present defects. So if you want, you can subtract some defects. If you want, you can add further impurities if you want to. So just follow this, it will be okay. And I would highly suggest you read everything. I am not reading because I created this thing. I know what that means in each step, so I would suggest you read this thing together. So before calculating like interstitials, one thing that we need to know is that we need these 4 files. When I was trying to calculate the DOS, as you can remember, for the unit cell and DOS, I actually mentioned that we need these 3 and this uh, log4 file for further investigation. So when we are considering the interstitials, we need to make sure that we have these all 4 files in our hand from the DOS calculation. So what I'll do, that I will copy everything from that folder to this defect folder here, and then I will try to create an electron charge. So for interstitials, as you can see, interstitial defects are the defect that is actually within that are not in the atomic position, but somewhere in between in the crystal. So you need to make sure that you have the perfect or proper electron charge density, so that you can find out the position where there are no atoms, and you can place your atoms there as an interstitial defect. Okay, so that is why all these files are required. So let's copy this file and just run it, and let it finish. Yeah, as you can see, like, okay, so all these different things are created. Now if you just come here in this file folder, defect folder, and refresh it, you will see that this file is created, volumetric data local extrema. If you want to see what is inside this file, just PyDefect print it. So the command is PyDefect underscore print, then you just mention it and hit enter, and it will show you. Okay, so now what I need to do is I need to add this interstitial. So the basic way to do that is that you use this command, and at the later section, as you can see, -I, that refers to the interstitials. So 1, 2, this sequence means that I am trying to create 2 interstitials. So if you want only 1 interstitial, just write -I, then 1, that will be all. If you need 3, then -I, 1, 2, and then space 3. Okay, and after you create the interstitials, just again you will have to run the command PyDefect ds. So what it will do, that it will update your this file, defectin.yml file, and it will add interstitials to that file. So let's copy this whole thing and just run it here. Okay, now I have everything I want, right? I have the impurities also, I have the interstitials also, vacancies also, so everything is here. So we are done with like adding these defects. So if you are in this step and you fall any non-primitive error, just run this command, and then start running everything from here till you reach here. It should be okay. So very well, so this is the step after at which we have added all the required defects. So this final file, defect.ml file that we have here in this defect file, this defect.yml file, it actually holds all the different types of defects that you will be using for further calculation. So this is like you are creating a, you could say, a register of defect, and you have not started calculating anything, just you have just mentioned which types of defect you want, what are the charges tests, and all those things. In our next video, I will create different types of folder using all these defects, and we'll try to simulate it, calculate it, and we'll see the formation energy diagram.